Let us start analyzing a rigid plane frame, orthogonal rigid plane frame by this stiffness method. As usual, the steps to be followed already I have given. Let us follow the same step. The first step is you have to identify the unknown member forces as well as unknown joint displacements. Unknown joint displacements you have to identify in terms of global coordinates, unknown member end forces in terms of local coordinates. First, let us define the unknown joint displacements for the frame in global coordinates. Here, this joint, it is fixed, there won't be any displacement, so unknown displacements are 0. Here, this joint, it is also fixed, hence unknown displacements are 0, they are all known. And since we are assuming all members to be axially rigid, this vertical displacement at these two rigid joints, they have to be 0. And since this member is axially rigid, whatever displacement horizontally which occurs here, same displacement should occur here also. That displacement let us call or identify as 1. Then of course rotation here it is possible, so we will call it as 2 and this as 3. This 1, 2, 3 are the coordinates which represents the positive direction of unknown joint displacements. So let us denote all these unknown displacement by matrix notation. Let us call it as D1, D2, D3 along these coordinates. So we will represent all the unknown displacement by D matrix, which is a column vector consisting of 3 elements, D1, D2, D3, and of course the corresponding corresponding loads, equivalent joint load also we have to work out. That we will work out little bit later after finding fixed end moment. Then unknown joint member end forces, that also we will just mark it. Usually I told we will take moments at the ends of members as the unknown forces. So in the clockwise direction in this fashion. So here there are 3 members, 1, 2, 3. So the local axis, if we call this joint as 1, this as 2, this as 3, this as 4, then the local axis for this member 1 will be 1, 2, 2. In this direction is the local axis. Here 2 to 3. Here we can take 4 to 3. These are the local axes which coincides with that global axis, whatever we have chosen for representing the unknown joint displacement. Global x, global y, rotation about z axis that we have chosen here. The unknown displacements in terms of the global axis. Here member axis, we have chosen this as the near end for member 1, this as the far end. Near to far end is the member positive direction of x-axis. In the same fashion, the arrow indicates the direction of the axis. This is the local axis. These are the member end forces which we have to determine. This is unknown member end forces which we have explained so many times. We call these as coordinate 1, 2, 3, 4, 5, 6, or the moments we call it as PM1, PM2, PM3, here along the coordinate 3, and along coordinate 4, PM4, PM5 along coordinate 5, and PM6 along coordinate 6. Therefore, unknown member and forces which we have to determine, let us represent by matrix notation PM, and the elements are PM1, PM2, PM3, PM4, PM5 and PM6. This we have to determine. So PM and D both we have to determine during our analysis. That's the first step. One is in global coordinate, another in local coordinate. This displacement we determine by using force displacement relationship first, that is P is equal to KD, where K is the global stiffness matrix in terms of this coordinate selected for D. So here 3 coordinates are there. The global stiffness matrix will be 3 by 3 for finding displacement. First we have to determine displacement, and then we have to determine the member and forces. Then the second step, we have to determine the fixed end moments corresponding to these member and coordinates due to given loading, that is fixed end moments. So that is, we have fixed end moment only with respect to the member BC or member 2, because that is the only one member which is subjected to this external member loading. These 2 members, member 1, it is not subjected to any member loading, therefore fixed end moments are 0. Whereas this member is subjected to member load of 90 kilonewton, therefore the fixed end moment here, it will be in this direction, that is anti-clockwise. Here it is clockwise direction, and this moment will be WAB squared by L squared. L squared, that is 90 into 4 into 2 squared by 6 squared. That is, I think, 19 into 4 into 4 divided by 36, that is 40. So it is in the anti-clockwise direction. So it is minus 40. Similarly, the moment here, it is 80. It is in the clockwise direction, so it is positive. Here in this member, there is no member load, so fixed end moments are 0. Therefore, PMF, the matrix corresponding to fixed end moments of whatever that in the local coordinate we have selected. So PM1 corresponding to coordinate 1, 0. It is 0, corresponds to coordinate 0, corresponding to 3 it is minus 40, corresponds to 4, 80, 5 and 6, they are 0. These are the fixed end moments we got. And we have a joint load here, that is horizontally it is acting. This load we can take 20 kilonewton, and that we have to subtract from this PMF in order to get this PD. So next, this PD we will generate, that is the load corresponding to unknown joint displacements. So this is nothing but the joint loads corresponding to the unknown displacement minus member length actions, fixed member length action. So that we will take it like this. So it is corresponds to unknown joint displacement, corresponds to one direction. Pj is there. Now it is coming to picture this joint load. 20 kilonewtons, it is in the direction of coordinate axis chosen. So it is plus 20 minus PMF, it is 0. There is no fixed end action corresponding to that. Here corresponds to 2. It is minus 40 because it is in the anti-clockwise direction. Corresponds to 3. It is plus minus. This is plus
40 minus 80.
This is minus 80 because minus of minus we have to take. Now it clearly is minus 40. Minus of minus is plus. Here it is plus 80. Minus of that 80 is minus 80. This is what we have to take. This is our PD which we have to generate. That already have taken here. So that is our, actually you can take this as third step. Equivalent joint load. Equivalent joint load. So the next fourth step, to generate K matrix, that is stiffness matrix and unit load member and matrix, member and forces matrix. So these already I have defined K matrix, how to generate coefficients of stiffness matrix, how to generate already I have told. That is, we have to go on applying unit load corresponding to each of those coordinates where we have to determine the unknown joint displacement one at a time and find the corresponding member and forces. So first here we will say, since there are 3 degrees of freedom, size of stiffness matrix, size of K is 3 by 3. Therefore, the stiffness matrix 3 by 3 matrix, you can represent it as K11, K12, K13, K21, K22, K23, then K31, K32, K33. These are the elements of the stiffness matrix. This we have to determine. So first, to find out this, we have to apply unit load one at a time along each of the coordinates. First, we will apply unit load along the coordinate 1. That is, this is the coordinate 1. We will apply unit load d1 equals 1. Not unit load, unit displacement, sorry, not unit load. Unit displacement will apply along the direction 1 and d2 and d3 displacement, we will keep it 0. d1 if I apply equal to 1 here, it displaces like this, in this fashion. This is 1, this is 1. We are applying unit load, unit displacement in the direction of 1 like this. So the members which are affected are this vertical member 1, 2. So here this gets displaced like this. Since it has to be displaced, there must be a force here, and that force we are going to represent it as K11. That is the force in the direction of 1 to cause unit displacement in the direction of 1. So here to keep this in equilibrium, here there must be equal and opposite. Again, to keep this further in equilibrium, there must be equal and opposite moment, which is in the anti-clockwise direction, because this will give you clockwise rotation. This has to be anti-clockwise. So here, this is the one which we have to determine, because this moment corresponds to coordinate 2. We will represent it as K21. But here also it will be there, but that we are not using in our computation, so I need not mention this. Here also, this we are not using in our computation, though it is there, that we are not using. But this we are using in the computation now, PMU, remember and moment. So this also we will represent that value. Whereas the other one, stiffness, we will identify by that notations, whatever we have used here. This is K11, K21, and this value will be 12 EI by 12 EI delta by L cube. That is 12 into EI is 2 EI, because this member EI value is 2 EI, delta is 1 divided by L cube, that is 6 cube. So this value, it comes to 24 EI divided by 216. So this comes to EI by 9. That is the value of the K11. And this value, it will be 6 EI by L square. That is 6 into 2 EI delta 1 divided by L square. So this becomes EI by 3. And of course, it is in a direction opposite to the coordinate direction chosen. So this will be negative. So for this member, we have little bit. This member also undergoing displacement. So that also it undergoes displacement like that. So due to that, on similar lines, here there must be a force equal to, this is K, this corresponds to 1 only, K1, unit displacement is given as 1 only, so it is K11, both are K11, we have to add it together for finding the net value of this coefficient. This is K11, so this is 12 into EI of this is EI itself, that is 12 EI divided by L cube. L cube is 3 cube, that is 27. So this is 4 EI by 9. And here there must be equal opposite force. This is a clockwise moment. There must be anti-clockwise moment generated to keep that in equilibrium. And this moment, it corresponds to our coordinate 3. So this we have to identify as K3 along the direction of 3 due to unit displacement along 1. K31. This will be 6 EI delta 1 divided by L squared is 9. So it is 2 EI by 3. So this is negative because it is in the opposite direction of the coordinate chosen. So this also will be minus 2EI by 3. Here this also will be minus EI by 3. That we will use later in the generation of PMU. So this is the first column of the stiffness matrix. K11, K21, K31 is this. All elements we got, so you can write it. The K matrix corresponds to the coordinate displacement given at 1, that is K11. Here this is 1, 2, 3. This is 1, 1. EI by 9, K11. Here it is 4 EI by 9. Right? These two, if I add it, I will get 5 EI by 9. That's the first element of this. And this 2, 1. 2, 1, here we have, it is minus EI by 3. That is the second element of that stiffness matrix of the first column. And K31, we have here minus 2 EI by 3. Similarly, P, this is of the K matrix first column. Similarly, PMU of the first column corresponds to this coordinate 1, unit displacement given. This is corresponds to these PMs, whatever it has to be generated. That is here, PM1 is minus EI by 3, and PM2, it is minus EI by 3, and PM3, it is, of course, I have not shown here. This is that this is 0, this is 0 because it has not undergone any displacement. So naturally it is 3 and 4. It will be 0 and PM5. That is this. This corresponds to D. That is minus 2EI by 3. And other one also minus 2EI by 3. These are the elements of that rectilinear matrix. The elements of first column. Next, again, let us give unit displacement along the direction of coordinate 2, keeping other two displacements in the direction of 1 and 3, 0. So that is the exercise you have to do for generating the stiffness matrix. This already I have explained, but again I am explaining in detail for the frame. So you just first give a sketch, you give unit displacement in the direction of 2, D2, in the direction of 2. This is that. If I give like this, so this has to displace in this fashion because it is the direction we have chosen. Here this has to displace in this fashion because this is how the direction of the displacement. So the members and here it has to be fixed. Here also there is no horizontal displacement. It is not going to move. Here also it is not going to move along direction 1, as well as 3 is also not moving. We should restrain those things as per this definition of stiffness matrix. Here the two members which are affected, as usual, the first member is this is affected. So this is that it is the direction is in this opposite direction. So it is like this. So this is how it has displaced. And for giving that displacement here, there must be a force in this direction, and here it should be in the same direction. And these forces already you know, this is 4EA by L, this is 2EA by L. For this member, this stiffness coefficient, it is corresponds to coordinate 2. So coordinate 2 and unit displacement is given corresponding to 2. So this has to be K22. And here when we give this displacement to this keeps on rotating in the clockwise direction to arrest that is to keep that in equilibrium, there must be an equal and opposite force developed. This is also very important, that is required because that is, there is a coordinate here 1. This force is in the direction of 1. That also you have to mark. So this is nothing but your K1, 2, because it is in the direction of coordinate 1 and unit displacement is given at 2. This K22 is 4EI by L, 4 into 2EI, that is 8EI by 6, that is 4EI by 3. So this will be of course 2EI by L, half of this value, so that is 2EI by 3. And this, it will be 6EI by L square. This is opposite to the direction whatever we have chosen. So it is minus 6 into 2EI, that is 12EI divided by L square. And this is 6EI, not 6. 6 into 2EI is 12EI. 12EI divided by L square, that is 36, that is minus L by
the table one is 12EI by L square, L cube.
That is 12EI by L cube. That is, displacement is given in this direction itself. That is 12EI by L cube. But here it is displacement generate, that is the force generated on account of rotation. So it is 6EI by L square. So that you have to be careful. 4EI by L, 2EI by L is unit rotation moments, and shear is 6A by L square. Whereas displacement, sway, that is displacement direction force is 12A by L cube, and rotation will be 6A by L square. There. Oh. So this is 4A by 3, 2A by 3, this is 6A by L square. These are the moments in this. Same thing, this member that is also getting affected, so that it moves in this fashion. So here, same formula, that is 4A by L. It is the moment generated. So this particular matrix coefficient, that is stiffness coefficient, is corresponds to 2. This corresponds to 2 when unit displacement is given at 2. This also K to 2, that's also K to 2, because both are same joint B. So that is rotation corresponds to same 2. So this is 4 into, this is EI, 2EI, 8EI divided by L is 6. So this is also 4EI by 3. And at this joint it will be half this value, that is 2EI by 3. And here also, because this is in the clockwise direction, there will be force generated which gives moment in the anti-clockwise direction, that is like that. And of course that force is not at all required for our computation. We will ignore it, let us not write that. So this and this moment is also required. This moment 2EA by 3, this corresponds to coordinate 3. That is coordinate 3. So that is why this is K3. Force given, displacement given is at 2, K3 2. So these are the elements. So the second column of K matrix is, you can write it, K11, K1, this is the second matrix, K12, K22, K32. K12 you got here, it is minus EI by 3. K22 you got here 4EI by 3, 4EI by 3, it is 8EI by 3, and K32 is this, it is 2EI by 3. These are the second column of stiffness matrix. First column, second column. This you have to write it individually like this, means it is easy for calculation. So this is that. On same lines, PMU for PMU matrix second row, second column, corresponding to that unit displacement given at 2 is the PM1's whatever corresponds to these local coordinates. Here it is 2EA by 3 clockwise. Here it is 4EA by 3. Then in this member it is again 4EA by 3. Here and here it is 2EA by 3. And of course that vertical member, whatever is there, the other vertical member, this it has not displaced. So here at this member it is 0, 0. So these are the stiffness matrix elements. Then you give the last one, you have to apply unit displacement in the direction of the coordinate 3. That is D3 equals 1 and D1 and D2. You have to keep it 0. First case, second case, third case. This exercise you have to do because that is the major part of this computation, nothing other than that. K matrix, PMU. Then only you have to use that equation. Where P is PD equals KD to find D, and this PM is nothing but PMF plus PMUD. So that's all. The other parts are only matrix additions only. here this you have to be careful and do it without any problem. Now you have to give D3 equals 1, so this has to move in this fashion. This is D3 equals 1 we are giving here. This has to move like this, 1, 1. So the members affected by on account of this displacement or this member BC and CD only, as we have done there. You can draw that particular free body diagram and identify all the coefficients. So here we have to give unit displacement and force generated is 4EI by L, and this force corresponds to that displacement, right? Displacement D3. So this force corresponds to 3 when
3.
For unit force is given at 3 itself. So this will be K33, which is 4 into 2EI. So it is 8EI divided by L. It is 4EI by 3. And here you will get half of that value, 2EI by 3. And to oppose this, there will be equal and opposite force here, which is not being used. Anyway, so let us not use that particular thing, right? That particular thing. So this other member, it will displace in this fashion. So again, here this force is 4EI by L, that is 4EI by 3, and this corresponds to stiffness coordinate 3 when unit displacement is given at 3 itself. So this is also K33. And here in the same direction, half this value, it is 2EI by 3. So this rotates in this fashion. So opposing this, there will be reaction. And mind it, here this reaction comes into picture, whereas this is not coming to picture because this corresponds to our coordinate 1. So this particular thing will be 6EI by L square. Because 4EI by L, 2EI by L, and this one is 6EI by L square. That is 6 into EI is EI itself, L square is 9. So this is 2 minus, of course. So this is minus 2EI by 3. And this coefficient is corresponds to coordinate 1 when unit displacement is given at 3. And of course other member, this vertical member, it is not affected at all. That is, forces are 0, 0. Now you can type that last column of stiffness matrix as well as PMU matrix. So that is K. The third column corresponds to this 1, 2, 3 forces. 1, 3. 1, 3 already here I have identified. It is minus 2EI by 3, and 2, 3. 2, 3 is, we don't have any 2, 3. Here we have, this is K2. So this corresponds to
second
coordinate 2, moment 2. So it is that force that corresponds to 2EI by 3. And 3, 3 is 4EI by 3, 4EI by 3. 8EI by 3, and PMU matrix on same line corresponds to this third coordinate unit displacement. So that is corresponds to these member and forces. They are that PM1, PM2, it is 0, 0, and PM3 is this, that is this 2EI by 3. And PM4 is this 4EI by 3. This you have carefully write. Then PM5 corresponds to this. It is again 4EI by 3, and 6 is 2EI by 3. So these are the stiffness coefficient and this. Now finally, you write the K matrix is given by all these columns, 1, 2, 3. All the 3 columns you put together, you will get that 1, 2, 3 matrix. That is our stiffness matrix, because here I told it's a 3 by 3 matrix of these elements. Those elements already have written.
So that
K11,
that PMU is only dependent on rotations.
PMU is only rotation you are taking. That's why I have not written anywhere else. The translation I have written only corresponds to coordinate 1, because it is wave frame only corresponding to that you have to take. Otherwise it is only, we can concentrate on rotations. So here it is 1, 1. K11 is, I will take EI by 9 outside. If I take EI by 9 outside, so this will be 5. K11, it is 5 EI by 9, EI by 9 I have taken outside, 5. Next, 1, 2, the other columns also we can write, it is minus EI by 3. Because 9 I have taken outside, I have to multiply by 9 inside within the column,
minus
so that
3.
will be minus 3. So next one is minus 3 into 2, it is minus 6. That first. Next, second one, again EI by 9 I have taken outside, so this has to be
minus
multiplied by 9, all this. So this will be minus 3, this will be
yes,
80 with the 3 is there, 9 by 3 is 3, 3 into 8, 24. Next, it is 2 into 3, 6. So this is the second column. The third column, here again multiply by 9,
minus 6.
you get minus 6,
plus 6.
here it is plus 6,
24.
here it is 24. So you make sure it is diagonally symmetric. Otherwise, you have to verify your calculation again. Always stiffness matrix is diagonally symmetric. PMU is not symmetric, don't bother about it. Whereas stiffness matrix, you have to make sure. Then you just write PMU also, because this is the major exercise you have to follow. And you should not do any mistake. This PMU matrix corresponds to those member coordinates 1, 2, 3, 4, 5 and 6 member and moments. We have generated that. Here I can take EI by 3 outside. So if you see the first column, EI by 3 I have taken outside. This is minus 1. Then minus 1 again.
0.
Next 0, 0. Next you have minus 2, minus 2. Then second column, it is 2. Then 4. Then 4, 2, 0, 0. Then this third one, it is 0, 0, 2, 4. Then here it is again 4, 2. This is your PMU matrix. This carefully, with peace of mind, without any mistake, you have to do. I have explained initially also, right? Without any mistake. So you have to follow that. Simple thing, it is nothing but much. You have to give unit displacement that you mark it in the mainframe. Then all the members which are affected that you mark it. And only stiffness matrix go on identifying that whatever that coefficient notation we have given here, that you have to identify, and there won't be any problem. And the PMU matrix, it is just only the moments at the ends of each member. That's what we have selected, the local coordinate. This, if you remember, generation of this, which is the primary nerve point of this problem, entire problem. Any problem for that matter, by stiffness matrix is calculation of stiffness matrix in global coordinates as well as PMU. That's the thing. And last step, to find unknown joint displacements. That will take up now. All these things I can take it out from the board, not from the skip her. So next step to find displacement, unknown displacement. So we have some force displacement relationship. We have PD is equal to K into D. Yes, go down. This PD, this is global stiffness displacement, and this K matrix, whatever we have generated. PD already we have generated, right? In the first step, here we have 20, here it is 40 and minus 80. You can refer to that first step. Here we have generated, that's the one value we got, is equal to K is this VI by 9 into 5 minus 3 minus 6, and then we have 24, 6, 6, and 24. This is the K matrix. DS, what we have to determine, that we have identified as D1, D2, and D3. So we have to find D. It is nothing but D1, D2, D3 is nothing but inverse of this matrix K multiplied by PD. Therefore, this is a simple calculation, last two steps. Whatever we have to determine, that we are determining straight away.
The PD matrix also, it's depending on D1, D2, D3.
Which one? PD matrix?
PD matrix.
B matrix.
PD.
This PD, it depends upon that only.
D1,
That
D2,
corresponds equivalent joint load. I told equivalent joint load corresponding to
D1,
displacement. Unknown displacement. Because that we are using here. Not the PMF and all those things. It is only equivalent joint load corresponding to unknown displacement, which is PJ minus PMF. That you have to be careful. This is nothing but joint load minus reverse of member.
The joint loads always it's in translation only.
The joint load, because it is acting at the joint itself, you need not reverse its sign, whereas member load is acting on the member and fixed end moment is reversing that. Again, we have to bring it back to original direction only. As if, that's why in that overhang problem, we took only the load, directly the moment due to the load as joint load. We didn't reverse it. In fixed end moment, we are reversing its sign. Of the action, reaction we are taking. That's why here, by finding the actual applied load, we have to reverse it again. We have to take it back originally. So that's the thing you have to be careful. Here, this inversion of matrix. So I have here, otherwise you have to invert it. So this will be 9 by EI into determinant of this. Determinant is R, of course, totally. It is 1 over 17 inverse of this is given by 1 over 17 into 45, 3, 10.5. 10.5. So this has to be symmetric. This is 3 and 10.5. And then next is this is 7. This is minus 1. This has to be minus 1. And here 9.25. So this is the inverse of this matrix. So this multiplied by PD, that is 20, 40, minus 8. So this is another exercise you have to do. So if you just multiply this matrix and this matrix, we can multiply because this is 3 by 3, this is 3 by 1, this column row is equal to this column. So resulting matrix will be 3 by 1. That is exactly the displacement corresponding to that. So this, if you multiply, you will get the displacement directly. I have the result here. It is 1 over EI into 10.6. Then I have 24.7. Then I have minus 33.5. These are the displacement values. B1, B2, B3. This is our first solution. Unknown displacement we have computed. Next, lastly, the emergent forces. So next step, we find number n forces. That is PM. That's what the notation we have used in the very first step. So we have the formula. We have PM is given by PMF plus PMU into this displacement. This is nothing but simple slope deflection equation. PMF, MAB bar or MBA bar, whatever it is. This is the coefficients of the matrix. 4A by L into theta A, 2A by L, theta B, then 6A delta by L squared, all that. This is exactly slope deflection equation, and these are the stiffness coefficients corresponding to those moments which we have generated. So this is nothing but PMS, we have already, this is the 6 by 1 matrix we have to get. So PMS we have already determined, that is nothing but 0, 0, minus 40, 80, 0, 0, 0. You can write it that you have already calculated. And PMU you have calculated here, that is AI by 3, A2, minus 1, 0, 0, minus 2, minus 2, that's the first column. Then second column 2, 4, 4, 2, 0, 0. That is the second column of PMU matrix. Third is 0, 0, 2, 4, 4, 2. So this is that PMU, whatever you have generated, into D. D you have worked out just now, that is 1 over VI into this 10.6, then 24.7 minus 33.5. Now we can multiply these two, because this is 6 by 3 matrix, this is 3 by 1. That 3 get cancelled, 6 by 1 you have to get. This is also 6 by 1. You can add the two matrix PMF, you will get PM. That's very simple, straightforward thing that we will complete it. So therefore, PM matrix. Therefore, PM, it is nothing but PM1, PM2, PM3, PM4, PM5 and PM6. That 6 end moments. That is nothing but. So this, if you can simplify, I have simplified value, because this you can easily multiply. Minus 1 into 10.6, minus 10.6 plus 2 into 24.7. So that is this. That divided by 3 plus 0. So that if you do that exercise, you will get here 12.9. Next, 29.4. Next, minus 29.4. Then 51.8. Minus 51.8. Then lastly, again, minus 29.4. These are the end moments. Here you can check always, that is, this is your MAB, MBA, MBC. That is 0. This is MCB, MCD, and this is MDC. So that also you are getting. Now finally you can plot the bending moment and shear force diagram. Analysis, there is no question of sway, non-sway, and all those things. All unknown displacements. at the joints, whether it is translation type or rotation type. That we are marking. Anyway, in the beginning itself, we are identifying unknown member and forces to be determined, unknown degrees of freedom or joint displacement. So corresponding to that, we are doing the calculation. It's a simple, straightforward procedure for which it can be easily programmed on a computer on this particular procedure without any hitch. So that's why it is very fast. For hand computation, it may be a little bit lengthy because it is 3 degrees of freedom. Maximum we have taken this problem, that is with 3 degrees of freedom, that is as per your syllabus, maximum one. So that is why this is for hand computation. The procedure is very tedious, but for computer usage it is very fast. Now for drawing the bending moment diagram, first let us mark all the moments computed. This is 12.9, this is 29.4, this is 29.4, this is 51.8, this is 51.8, this is 29.4. Now you can compute. First I will take this vertical column AB. Here n moments are the 29.4 and 12.9. There is no member loading, right? Hence only the shear force corresponding to this only we have to compute. You take this shear moment about this point, so this shear into this height 6 meters, right? Then you can take the algebraic sum of the moment. So that value also I have this shear value, I think 7.1 you are going to get here. Here it should be equal and opposite because sigma v has to be 0. So therefore we can plot the bending moment diagram. So this is 29.4, 12.9, just like that. So this is your B and D, 12.9 and 29.4. And shear force diagram, it is just a rectangle. Right. So we are moving like this in our member coordinate is like this, A to B direction. This is the axis, member axis. So when this is the axis, this is right side, that is left side, or vice versa. If you see here, this will be right side, left side. Accordingly, you can fix the sign of that particular shear force. It is 7.1, 7.1. I think this is negative. This is SFT. That is for member AB. Next for member BC, you have a load here, 90 kilonewtons, and you have end moments, that is PM3, PM4, 51.8, no, 29.4.
29.
PM3, PM4, that is 29.4 anti-clockwise. Then this is
51.8.
clockwise 51.8. So you can find out the shear forces by taking moment either at this left hand or right hand. So the shear force, whatever we are able to get is 26 point. I don't have correct value.
Yes, sir. 90.
Correct.
63.7, 26.3.
This is 26.
Sir, 26.3.
This is 26.3.
3.
This one
63.7.
63.7 will take it, right? So the bending moment diagram for this, you can plot it. Here 29.4, here it is 51.8, join this and this. So that is the fixed moment diagram. Free moment diagram is WAB by N. W is 19, 4 into 2 divided by 6, that is 120. it is definitely more than 63.7. So this is the net moment diagram, negative, positive, negative. This is net bending moment diagram in BC. Then shear force diagram also you can plot it. Here if you take it, here it is upward positive 26.3. Here it is negative 61.8. From here to here it is constant. Then you are getting
63.7.
90 kilonewtons it comes down.
This is 63.7.
Oh, that's right. This is
63.7.
This is 26.3, 63.7. This sum has to be 90.
Yes, sir.
It has to be. So this is positive, this is negative, this is SFT. BMD and SFT for
BC.
member BC. And lastly, member A, B,
CD.
CD. You can plot it. CD, we have these moments. Here it is anti-clockwise, 51.8. Here it is anti-clockwise, 29.4. Here the reactions, you can find out the reactions. Of course, I don't have here. So you can find out that particular reaction. So only the bending moment diagram we can plot it. This side it is 51.8, 29.4. The bending moment diagram it is like that. So this is BMD and shear
value is 7.4.
7.4. Okay. This is like this.
Yes, sir.
Whatever it is, this has to be
7.4.
this way. So if it is 7.4, it also has to be a rectangle. That is yes. So this completes the complete analysis of this both sway and not sway all put together. So this is the step you have to follow in analysis of any rigid orthogonal frame. Maybe unequal leg, what we have taken here like this, or equal leg, or symmetrically loaded, unsymmetrically loaded, all problems, same procedure, absolutely there is no change. You need not have to bother, same procedure, only K and PMU. You have to generate property.
Sir, for the same problem, if joint load is 0, then here the PD value we have to take 0.
Which
in
one?
first translation.
If this is not there,
Yes, sir.
Suppose. Then it is only, it is rotation only.
Rotation
It
only.
is rotation only.
But PD we have having
Actually,
3D.
but D will be D1, D2. That corresponds to rotation here, rotation here. That's kinematic indeterminacy. First step, when kinematic indeterminacy you are determining, that itself is your coordinate for the displacement. That 3 degrees of freedom I am allowing at each joint. Very first step you can see for the generation of stiffness matrix. If this load is not there, but sway occurs, this coordinate you have to take because it is moving. That is moving only in the computation of PD.
PD we are able 0.
Load is 0. But in the computation of K matrix, we have to generate stiffness matrix corresponds to this degrees of freedom as well as two rotations.
And D also D1, D2, D3. D1 is translation.
D1 will be automatically whatever value you are going to get.
Yes, sir.
Because this is unsymmetric, don't be under the impression this will not move at all. It has to move. This I told I think in Connie's method also. Even if, don't be under the impression, if horizontal load is there, then only frame is sway.
The only change is in PD by computation.
PD only.
20 will become 0.
It doesn't matter. 0 is matter. Computation. This D1 definitely you will get.
Yes, sir.
D1 value definitely you will get whatever that no horizontal movement is there. Because it is sway, that is horizontal movement will be there. It will not be definitely 0. But that gets redistributed among the other members during that process.
Yes,
right? That you have to be very, very careful. So with this, we have completed almost analysis of all kinds of frames. Now we have to concentrate on pin-jointed frames. Pin-jointed frames, that we will take up maybe on Thursday's class. We will close it.
Thank you.